All right, well, thanks everybody for coming bright and early in the morning to this short course on optimization. So my hope is to give you an introduction and an overview of what, we have someone who should be,
please.
I can mute her, I think. All right, so to give you an introduction and an overview to what Yifeng mentioned is a pretty hard topic, but I think also is very easy to get a general sense of. So I want to start by talking about the applications of optimization. And that is basically, arguably, everything. You'd be hard pressed to find an engineering application that doesn't rely in some way on optimization. So just some examples, car manufacturers are deeply driven by optimization. So they have to optimize fuel efficiency, safety, cost, and similarly, airlines have similar demands that they want to optimize. So for airlines, fuel optimality is crucial to their overhead, as are other optimization problems, such as the rather unpleasant optimization problem sometimes of how many people they can fit in economy and how much they charge us for tickets. And parts manufacturers all have to rely on optimization, or at least benefit from optimization. So optimizing the strength of a part, minimizing points of wear and stress, and optimizing materials costs, all are beneficial to parts manufacture. Aerospace is an area that relies very profoundly on optimization. So aerospace has to take into account all the other things I already mentioned: fuel, safety, costs, wear, materials costs. And they also have to optimize this sometimes very dynamically. So they have to optimize their trajectories. The Apollo 11 trajectory to the moon, for example, was a major feat of optimization. And so in that case, you're optimizing fuel, because fuel is incredibly expensive to take into space. And you're going to find optimization not just in engineering applications, but underlying many, many other things. So many of the laws of physics can be explained in terms of optimization. So these are optimal solutions, and that's what creates the laws of gravity, the behavior of light through different mediums, and many of the laws of mechanics can be rephrased as the solutions to optimization problems. And then, you know, a not very surprising application, much of economics is driven by optimization, trying to optimize your profits and manage your portfolios in an optimal way. And you're just going to find this in every area: chemistry, biology, things fundamentally driven by optimization. Optimization is also the foundation of some applications that aren't even necessarily labeled that way. So you might not realize that optimization is their foundation. For example, curve fitting. Curve fitting is an act of optimization. Linear regression, least squares, polynomial approximations, any fitting to an orthogonal set, Fourier series. All of these can be explained as optimizing a certain metric. So, you know, least squares might optimize your output error given a predetermined curve. So these are all instances of optimization. Another main application that is optimization is neural networks. The terminology of neural networks doesn't always spell this out, but when someone talks about training a neural net, what they mean is solving an optimization problem. So a neural net is made by putting inputs through a series of layers. Each of those layers has some weights. Training a network is optimizing your weight values. So neural networks are a big optimization problem. And then finally, for AI, the topic of this REU, optimization also fits in just about every part of it, even parts that have other concerns ultimately. So first of all, machine learning, neural networks and the like, those are all driven by optimization. If you're doing reinforcement learning, you're solving an optimization problem. But questions of stability and estimation, filtering out noise, while those don't necessarily in the end optimize something so much as stabilize something, their mechanics, the way that you perform them is derived through optimization. So optimally filtering out something, optimally regulating something to a stable control point. And then of course, dynamics and control are optimization, and often motion planning, telling that robot where to go, is driven by optimization. So optimization is a giant topic, apparently, and it applies to just about everything. So we have incredibly diverse applications. And that with that diversity comes many, many numerical methods. So in that sense, optimization can be very challenging. However, optimization is actually not that hard to characterize as a problem. And so that's what I'm going to focus on a lot in this short course, just characterizing optimization problems in their main features, the components they all share, and then talking about the critical features that distinguish them. So these critical features are going to distinguish what sort of algorithms you apply and what sort of methods you look for. And once we characterize these problems, we can name some major problem types. And hopefully this will give you a bit of a roadmap so that if you encounter one of them, you know where to look and what kind of algorithms you're going to have to apply. And so I'm going to give an overview a little bit of some analytic and algorithmic approaches, but this is where the topic gets a little bit too big for one short course. So my goal, again, there is to give you a bit of a roadmap so that you can go and find your own problem-appropriate methods. While we're talking about algorithmic approaches, we're also going to do a little bit of hands-on at the end. So I'm going to show you guys some of the tools of Matlab's optimization toolbox, which is a very powerful tool for optimization, almost too powerful. In my day, you had to do a lot more of this on your own, but now actually Matlab has a wonderful GUI that can lead you to a bunch of the algorithms that you need for these. So that's the goal of today's short course. And I don't know if it's going to take 2.5 hours, but I know that I will have at least one break in there because 2.5 hours is a pretty long time. The chat says, used to have to triple integrate uphill both ways on an abacus. And, you know, that is exactly how I felt when I discovered this optimization toolbox GUI in my day. Let's start with characterizing these problems, because I really think that you can characterize all of them with just about 3 features. And they're going to have different implementations of these 3 features. And given those, you can label just about every optimization problem. So the first feature is that every optimization problem has to have a quantity that you want to optimize. So depending on the area, you're going to encounter slightly different terminology about this quantity. But it's all just one function, one numerical output, let's say, that you want to optimize, minimize or maximize, either way. So that might be called cost function, the objective function, it's your performance metric. In something like polynomial fitting or least squares, it might be your error function that you want to minimize. In neural network training, you might call it a loss function. In almost all cases, though, these are just going to be a single function. And I'll elaborate a little bit. There are, different outputs just than f of x. But one thing that almost all optimization problems have in common is that you might have many, many, many inputs. But by the nature of the task, that there's something specific that you want to optimize, you're only going to have one output. There are multi-objective optimization problems, but they generally go forward by finding some way, maybe a weighted sum, to turn it into one objective function. So every optimization problem has a single output quantity that you have to optimize. And this can be part of the challenge of a design challenge for engineering problems. The choice of your objective function, let's call it, immediately impacts what kind of solutions, if any, you have. So for example, on the left, if I chose my objective function to be that linear function on the left, and if I didn't bound my domain, then there wouldn't be an optimal solution, neither a minimal or a maximal. I would always be able to make it more or less. On the other hand, another problem you might have is that it doesn't necessarily have a unique solution. So on the right, you see one where there are two obvious minimal solutions that look to be identical. So what we get to pretty quickly by looking at objective functions is the question of what is a solution. So when we're optimizing, what is the optimal solution? This actually ends up being a really important question for a lot of the theories and the algorithms. So one way to look at it with this picture in this domain is that the solution on the left would hypothetically be the best if we were minimizing. So that's obviously the minimum on this picture. But the one on the right has a certain quality to it that we might appreciate. So while it's not the best in the entire picture, this one is the best in its neighborhood. And so this concept is a very important concept when we're talking about what kind of solution we have. So as far as the picture goes, the one on the left would be the globally optimal solution. And the one on the right is what we call locally optimal. So it's the best solution in its neighborhood. A sort of dirty secret of a lot of optimization techniques is that for the most part, most of them can only guarantee or find local solutions. This is a widespread problem. So the problem of global optimization is much, much, much more challenging than the problem of local optimization. And so whenever you're reading, a guarantee for an analytic solution or a computational solution, you should squint really hard and see if it's really saying global optimal or if all it's really guaranteeing you is a local optimal. Because this isn't always clarified by the people. Those are straightforward ways that the objective function shapes what kind of solution we're looking for. The type of objective function also impacts computational methods, demands, and the guarantees. So there is, obviously, in the computational side, you could have a much more difficult to compute objective function. So a neural network, for example, to compute its output function, you have to run it through the whole network. So that can be a pretty high dimensional computation. Other ways that this can impact it is that you could have a linear objective function or a nonlinear objective function. This actually makes for really different algorithms that can be available to you. You can also have a smooth versus a non-smooth objective function. So in the mathematician's dream case, you would have an infinitely differentiable, perfectly smooth objective function, in which case many algorithms would have some convergence guarantees. But in practical applications and in reality, you might have a very unsmooth, a jagged, non-differentiable objective function. And then you can run into a lot of numerical difficulties. And then, of course, there's also the idea of convexity, which I'm not going to get into the mathematical details of too much, but just think of it in terms of, whether you even have this guaranteed convergence and whether you have a nice local value for it to go to. And convexity is often a demand of convergence. So you have many algorithms, but whether they're guaranteed to work can depend on a lot of these properties. Feature number 2 that fundamentally determines the problem is defining your variable space. So you want to minimize this function, f of x, but what are you allowing x to actually be? So just an easy example, X might be bounded. So if we go back to this one and we demand that X is greater than or equal to 0, then that solution on the right side suddenly becomes the best solution that we could have. So bounded or unbounded is a fundamental feature or a fundamental way that we can define our variable space. Another important distinction that separates a lot of problems is whether you have a continuous space or whether you have a discrete space. So discrete spaces, you can just map them to integers. So do we have a continuous real number, for example, or do we have a set of integers? And also, kind of related to bounded or unbounded, do we have connected or disconnected regions that this is in? We can just keep getting more elaborate here. Are we talking real numbers, complex numbers, rotation spaces, other groups? It can get defining your variable space and how it constrains your optimization problem can get pretty involved. And of course, it determines your answer. And a final distinction there is whether we have finite sets or infinite sets. Am I optimizing over, 3 choices, or is there actually an infinity of choices? So this feature too is fundamentally related to the third feature and can be kind of interchangeably defined this way sometimes. And the third feature is constraints. Almost, I think, more than any of the other features, constraints are what define an optimization problem. If you think of some of the earlier optimization problems I mentioned, the very easy ones, like, for example, a car trying to optimize something. Say you're trying to optimize the path that you're following on a car. For example, minimize the time it takes to get from A to B. If you didn't have constraints on that optimization problem, it really wouldn't make sense. If you could drive your car infinitely fast, then A to B is an instantaneous transportation. It's the constraints of your car that make minimizing that time from A to B meaningful. So that could be the constraints of the road, the constraints of your acceleration, your fuel constraints. All of those constraints define the problem. And we can see pretty quickly how those constraints can completely change what your solution is, even as your objective function stays the same. So we've seen that this would be the best solution for X greater than or equal to 0. But if we added the constraint that your objective function must be, in this case, I approximated that -3, but let's say greater than or equal to -3, then suddenly these 2 points come up as your solution, right on the boundary. If you changed it to less than or equal to -3, then we're back to that original global solution that we found. So just the constraints can completely change how many solutions you have and where those solutions are. So these major problem distinctions, let's summarize as we've seen unconstrained versus constrained optimization. You can have linear objectives and constraints versus nonlinear objective or constraints. I wanted to just separate it into those two, but quadratic is a big enough area for me to mention it. Or you could have a quadratic objective function, and that has its own methods available. And you can have continuous versus discrete. Now, with those major problem distinctions, we can label a lot of famous methods. All of these methods are kind of comically labeled called programming. And this was actually because in around the 50s, programming was a very well-funded buzzword. And a lot of researchers started calling all of these methods programming. So they kind of, they age a little bit awkwardly in this era of other programming. But there's nonlinear programming. So sometimes the acronym for that is NLP. And that's the process of solving this problem on the right side, minimizing some objective function, subject to some possible constraints there. So you can see that constraints can be equality constraints or inequality constraints. And we're going to, I'm writing this in terms of minimization, but a quick thing to learn about optimization is you can switch everything to minimization with a single negative sign. So whether you're working with minimization or maximization, doesn't matter. So nonlinear programming is when those are nonlinear. So specifically your objective function, and those constraints could be nonlinear algebraic constraints. Linear programming, an equally widespread and very famous procedure or set of procedures, is when those are linear. And this happens surprisingly a lot. And also you can take a nonlinear problem, linearize it, and have a linear problem. So these are, very related methods here. And then it's worth mentioning quadratic programming, where you have a quadratic objective. This is actually underpinning a lot of different algorithms. Even NLP algorithms will be secretly using some quadratic programming. And finally, so those relate to the linearity and the nonlinearity. And then you can basically add on another word if you're doing discrete. So these terms alone tend to assume that you have a continuous variable space. If you have a discrete variable space, then you're doing integer programming. If it's linear, you're doing integer linear programming. So I think you get the naming idea there. And then good to mention is mixed integer programming. And that's when you have a mix of quantities that are integers and quantities that are continuous. So a likely example of that is airlines. So when they are doing whatever terrible optimization problem they run on airline customers, they're minimizing or maximizing with respect to a discrete number of plane riders, while at the same time optimizing quantities that are probably considered continuously, such as fuel, or you could kind of consider fuel costs to be roughly continuous. So that would be mixed integer programming. So that gets us quite a lot of names, not all of them. And each of these types of programming, so the procedures for solving these kinds of problems, come with a whole bunch of different algorithms or conditions that you can try to apply to your problem. But so far, everything that I've mentioned falls in the category of finite. So that brings us to the last distinction that we've mentioned, which is this idea of a finite optimization problem versus an infinite optimization problem. So I want to talk about infinite optimization, infinite dimensional optimization, and maybe give it some more clear labels other than infinite dimensional. But first, let's be clear about what finite dimensional is. So finite dimensional, let's give some examples of finite dimensional optimization. So optimizing a 3-variable function is a finite dimensional problem. Even when x, y, and it's like that last one is supposed to be x and it's an x instead of a z, but x, y, z. This has 3 variables that we're optimizing. And even if those variables might be over a continuous space, so in some sense, you could kind of think of that as an infinite possibility, we call this finite dimensional. So there are 3 variables that we're trying to optimize. So kind of similarly, if we were going to optimally calibrate a parameter or a set of parameters, that would be a finite dimensional problem. Training the weights of a neural network is a finite dimensional problem. It's a very large finite dimensional problem. You might have hundreds, thousands, goodness only knows how many Google weights we're at now, but you might have a lot of weights, but it is, at the end of the day, a finite number of weights. Another famous finite dimensional optimization problem is the traveling salesperson routing problems. So the traveling salesperson usually wants to minimize the distance or the time to get to all these cities. Squares would be the cities. And you have to hit each city once. Variations of this problem actually come up a lot for companies like Amazon. when they're trying to route their drivers to deliver all their packages. That is, if the roads are the edges here between your cities or between your homes, that's a finite dimensional optimization problem. But it's a notoriously hard and large finite dimensional problem. So as especially these last two examples show, finite dimensional does not mean that it's a small problem. And it doesn't mean that it's going to scale well. In fact, this traveling salesperson, that's going to be NP hard. You can't even solve it after a while. It gets exponential. So it doesn't mean that they're small, but it does mean that you have a finite set of values to optimize. So here's an example where you don't have a finite set of values. And that is if you want to optimize over an entire curve. So a famous example of this is Dido's problem. Dido was the founder of, so goes the story, the founder of Carthage. And when she arrived, she asked for a piece of land, and they gave her one continuous hide, and she had to, optimize the area of the land that she could enclose with that one long strip of hide. Obviously, this story is probably a little bit to be taken non-literally, but the problem became known as Dido's problem. What is the closed curve that has the maximum area for a given parameter? So if we're going to optimize this problem, we have an entire curve, an entire function that we could optimize over. And this is what we mean by infinite dimensional. So you can kind of think of a function as an infinite collection of points, and we are going to optimize each of those points. So this is an infinite dimensional problem. And there are other really famous examples of this kind of infinite dimensional problem. So geodesic curves. Geodesic curves are another optimized curve. They minimize the length of a curve over a curved surface. So if you have a flat surface, then the curve that minimizes the distance from A to B is going to be a line. But if you have a sphere, for example, then you get these geodesic curves. And geodesic curves also come into play with the theory of relativity there. So you get the paths that many of the planets follow can be explained as this optimal curve solution. Another famous example, and in fact, this is perhaps more mathematically famous than something you might have encountered, is the brachistochrone problem. So let's see if this video will play. Okay, good. Some of my video links have been dying. So the brachistochrone problem wants you to asks what curve there, so you probably can't see my mouse. So what curve would create the minimum time curve for these little balls to fall down? This problem has a really famous role in the history of math. So I think it was first asked by Galileo, and Galileo guessed the answer wrong. Galileo thought that the curve that would minimize the time for those balls to fall down would be a segment of a circle. And it turned out to not be the case. So this problem was then famously asked by one of the Bernoulli brothers back in the days when mathematicians wrote themselves all sort of, challenging publications and letters back and forth. And it was answered by Newton and Euler and Lagrange and just a whole bunch of famous mathematicians then put in answers to this problem. And the methods that they developed to try to solve this brachistochrone problem became known as the calculus of variations. So the calculus of variations is another major area of optimization. And in the calculus of variations, you're going to optimize a whole curve. So that's your variable set. And because you have to optimize over a whole curve, your objective function is going to be something that depends on the whole curve. So generally, you're going to see something like an integral. So this integral, in the brachistochrone problem, you would do an integral of arc length over velocity. It's actually a rather complicated one. That's a terrible example, but you could do an integral that did the length. You could do an integral that does the time, if you consider this a trajectory. So in calculus of variations, for about 100 years, let's say, was the peak of this infinite dimensional optimization. But although it solves a lot of problems, and there are other examples, you actually will find solutions from the calculus of variations in a lot of architecture. There are some really beautiful curves that come out of the calculus of variations, but it doesn't quite cover everything that we might want when covering a curve. So in the calculus of variations, you can generally make whatever curve you want. In fact, it's called the calculus of variations because when you're optimizing, you can take y of x and vary it in any spot along the curve to try to get a better curve. But in many applications, we might not have full control over what that curve is. So an example would be, say you want to optimize the trajectory of a car. So you want to minimize, let's say, the distance that car actually expends getting from A to B. So you want a really nice curve. Maybe you're going around a corner, for example. So it's the curve, let's call that x of t. It's the trajectory of the car that you're trying to optimize. So in that sense, it is a little bit relatable to the calculus of variations. You have a whole curve and you want to optimize over the curve. But you don't have total control over that curve. You can't just move the car wherever you want. Your control over that curve is your input into the car. So you have the gas pedal, the brake pedal, you have the steering wheel, and those are all constrained by the weight and acceleration capabilities of your car. So what optimal control looks at, optimal control you can kind of think of as the next step from calculus of variations, is you want to optimize a curve, in optimal control usually called a trajectory, but what you can actually optimize is your control input into that curve. So when I'm optimizing my car motion, what I'm really optimizing is my use of the steering wheel and my use of that gas and brake pedal. So this creates what could be thought of as a dynamic model. You'll often see it as an ordinary differential equation, but the dynamic model could be a lot of different dynamic models. There are PDE models, there are discrete models. What they have in common is that you're only able to input that control u, and that defines what family of curves you can create. So this is a major area of optimization. Just like with the calculus of variations, you end up with an integral objective function. And so you can think of a lot of different things that you could optimize using this. So you can do some running time costs. So for example, fuel expended over time. And when you integrate that rate of fuel expenditure, you get total fuel, and then you might want to minimize it. I assume you want to minimize total fuel. I'm not sure why you'd want to maximize it. And you could have some, you could also think of that as an in-time cost. Actually, these are interchangeable mathematically if you ever get into this. So, the amount of fuel you have left at the end, for example, or you could have a minimum time cost, which isn't quite represented by this formula on the top. So a lot of different costs, generally characterizable here by some sort of in-time or integral cost. But without getting too buried in the details, I wanted to provide an example of just how neat optimal control problems can get. And I think this example also shows the feature that I said was really profoundly defining of an optimization problem, which is that optimal control problems are really defined through their constraints. And the constraints in an optimal control problem are that dynamic system. So the limitations of your car define the optimization problem almost more than anything else. And a really fun example of that was actually given in the last decade or two with NASA. So NASA had a problem with the International Space Station. The International Space Station is, a modular space station that we've had up in space since, I think, the year 2000. And it's a multinational collaborative project between US, Russia, Japan, Europe, and Canada. And this will come back to be relevant. So one challenge that the ISS has, so the ISS actually orbits the Earth a little over 15 times a day. And as it does this, it has to control its attitude. And attitude in this sense, you can think of as orientation. So the relative orientation of the ISS with respect to the Earth. And it has to maintain this orientation both for communications and also for its solar panels. And this involves both regular maintenance of it, regular control of it to keep it oriented, but sometimes also larger adjustments to reorient it. This can also be really challenging because the ISS has changes in altitude, so height above the Earth, and also in payload. So it's sometimes weighing different amounts. So let's see if this video works. Oh, there we go. Okay, so here is an astronaut briefly talking about this problem.
We're on board a spaceship. Which way are we pointing? We have to control which way we're pointing because we're solar powered. And we have to point our solar arrays at the sun. We have to control which way we're pointing because we want to be able to communicate with the Earth. So our antennas need to point the right way for communications with satellites. We have to control which way the space station is pointing, even while we're asleep. So we have sort of like an autopilot, and whatever we set it in, it'll keep that attitude going, just like in an airliner. And we can control it as the crew while we're awake using this display right here. It can also be controlled by the folks in mission control on the ground, either from Moscow or from Houston. But how do you actually turn the space station?
I'm going to stop him there because he's about to spoil where we're going. So the way they turn the space station now is different from how they originally did some of their turns. So there are two main ways to control the International Space Station. There are thrusters on the International Space Station, and there are also 4 control moment gyroscopes. And originally, the control moment gyroscopes were thought to be usable only for kind of smaller adjustments. So they could help maintain the attitude, but when the larger readjustments were needed, they needed to use the thrusters. And these two different ways to control it have some different features that were pretty relevant and kind of annoying from the perspective of having to use those thrusters. So the control moment gyroscopes used electricity, which the ISS has solar panels, so that is a renewable source of energy for the ISS. The thrusters use fuel, and fuel is incredibly expensive to transport up to the ISS. Also, and perhaps actually more motivating for NASA to look into this problem, the thrusters are controlled by Russia, and the control moment gyroscopes are controlled by NASA. So every time NASA needed to do a major adjustment, they had to coordinate with Russia, which was found to be less than ideal by some of the people at NASA. So NASA then asked the question, what if we could control it all with the gyroscopes? And this is a great example of an optimal control problem. You have some metric that you want to optimize. Here it's actually, I'm not sure exactly. So, you could say fuel or energy, but let's say we just wanted to minimize the time to do the reorientation. But what really defines the problem is what inputs of control you have available and the dynamics of the system. So the thrusters are one input of control with their own dynamic. Gyroscopes, you can imagine, have a much more complicated nonlinear dynamic. And you have to take advantage of this dynamic to come up with the optimal answer. In fact, you have to use both the dynamics of the gyroscopes and it turns out the dynamics of the station itself. So the momentum of the station and the dynamics of the gyroscopes. And so a real feat of optimization that then happened was that they managed to model this as a really high dimensional nonlinear optimal control problem and find solutions that safely would do large reorientations of the International Space Station using this synchronized, very beautiful collaboration between the gyroscopes and the momentum of the station itself. So this is a great example of an optimal control problem because it shows you how difficult it can get. So you can imagine, I'm not showing you those equations of the gyroscopes, but that is, 4 gyroscopes in a giant space station is a really high dimensional nonlinear problem. And it also shows you how powerful, though, optimization can be, because I think the idea that you could safely reorient the International Space Station using just these little gyroscopes was very surprising to everybody. And so this maneuver was rapidly adopted by NASA and is now how they move the International Space Station. So this problem, like I said, is very much defined by its dynamics. And other things that define optimal control problems are same things that we would use to define these other optimization problems. So constraints, magnitude constraints, fuel is a good magnitude constraint example. So you have only a limited amount of fuel. And you might have algebraic constraints. So an algebraic constraint could be the path that you have to stay in. So a road, if you were going to model that, would be often an algebraic constraint on the problem. And then actually part of the difficulty of control in many optimization problems is that you can start getting more and more elaborate here. So you could have integral constraints, you can have boundary constraints, you can actually have a lot of components in an optimal control problem. But just like with the other problems, we can then kind of solidify this back down and concisely summarize it again. So it's not too much longer to state than any of those finite dimensional problems. And just like them, we characterize it by what cost function is and what our constraints are. And within those constraints, kind of implicitly in this write-up, also what our variable space is. So I wanted to give that overview, and now we have kind of, I think, all the main areas of optimization, at least for the sake of this lecture. So we've looked at finite dimensional optimization, and we've seen examples of infinite dimensional optimization with the calculus of variations and optimal control. So now we've named a bunch of names, and it would be good to talk about what kind of solution methods we actually use to solve these. And in a sense, getting into the details of the solution methods is outside the scope of a shortcut course. But I think giving a really general idea of where the solution methods are coming from is really, can be done on a really elementary level. Because surprisingly, a lot of optimization all comes from the same kind of approaches. Of course, that's a very mathematician way to simplify it, as they all then flower into very difficult challenges that have their own idiosyncrasies. But we can kind of talk about the methods, I think, using some shared terms between them. And so the first distinction you can make is whether you're going to use an analytic solution method or whether you're going to use a computational method. And what I mean by that is an analytic method would be the ideal case where maybe you could solve a system of equations or solve some procedure exactly to come up exactly with a solution. So that would be an analytic method, if we could write an equation and exactly solve it. And there are, for many problems, analytic tools available. And I think they all come from a really similar intuition that we can talk about just using calculus. So I want to talk a little bit about what kind of analytic conditions we would have if we were just back in the world of calculus. So let's talk about, let's consider just a real valued, continuous function, unconstrained, and a single variable. And if we were going to solve that, so that seems like, kind of stripping away most of the challenges. Let's see if we can solve that. And starting with that, calculus provides pretty easy conditions that you've all probably encountered by now. So if I was going to look at an optimal solution, and actually this is a good revisit of something that I claimed before, which is that most methods can only tell you whether it's a locally optimal solution. Calculus has pretty easy conditions to characterize locally optimal solutions. And we can kind of just see them visually. So if something's going to be a locally optimal solution of a minimization problem, let's say, it's going to sit at the bottom of one of these little valleys. And a way to say that in math terms is actually that it's at a point where the derivative is 0. And you can actually prove that using Taylor series, which I almost included in this lecture, but I think might get a little bit dry. But you can prove this condition using Taylor series, so Taylor series expansion of the function. You can show that if it's really a local minimum, as in there's no neighboring point that's any smaller, then it's going to satisfy the condition that the derivative f prime of x here is going to be 0 at this point. But as the bottom two plots show, a 0 derivative doesn't assure that you're actually at a minimum. So here on the left, you have a 0 derivative also as a feature of a maximum point. And here on the right picture, that point in the middle has a 0 derivative, but it is neither a minimum or a maximum. So a 0 derivative doesn't assure a minimum. We call this a necessary condition. So it's a necessary condition to be a local minimum that it has a 0 derivative. And this is in contrast to a sufficient condition. So a minimum, having a 0 derivative isn't enough to say that it's a local minimum, but it is necessary. So any solution that has a 0 derivative is, let's say, a candidate solution. We could look at it, it might be a minimum. It at least has the necessary features of a minimum, but not sufficient. So that condition isn't enough to say that it's a minimum. Calculus does provide us with sufficient conditions if your objective function is smooth enough. So if you can take the second derivative of your objective function, then calculus actually provides us with the sufficient condition also to say that it's a minimum. And if it satisfies the necessary and sufficient conditions, then we know that we have a minimum. And then just kind of a note here, in dimensions, this is very easily extendable. So you use the gradient instead of the derivative, and then you have a positive definite condition on the Hessian. Just to mention that, but don't worry about that. So let's just, let's do just a really simple example from calculus to make sure we have the intuition about this necessary and sufficient conditions right. Because this intuition actually then applies to all the optimization problems that we've talked about. So say we're gonna minimize x squared. So f prime is 2x. We could solve this. So this would be an analytic method. We're gonna find the value, we're gonna find that minimal point. So we solve, f prime equals 0. We find that it's at x equals 0. Now we're going to do the second derivative test. F double prime there equals 2, and that's greater than 0. And so using these analytic conditions, we have solved for the minimal value there. And oops, looks like I have those slides twice. Okay, so let's do that same analysis for negative x squared. And so if we do it for negative x squared, we first solve for the f prime equals 0, and we find that same solution. So x equals 0 is a candidate solution to be a minimum. But when we apply that sufficient condition, we find that it doesn't satisfy it. And so as we would want calculus to say, 0 is not a minimum of this function. And similarly, you can see how it fails where it should fail here. So it also finds x equals 0 as a candidate solution for this x cubed function. But if you apply the second derivative test, it equals 0. So it doesn't satisfy the positivity condition. Okay, so this is a little basic. However, what's great about optimization is that this kind of basic analysis, at least, let's say metaphorically, applies to all the other optimization problems as well. So let's just talk about it in terms of necessary and sufficient conditions. So here would be kind of a summary of your analytic options. Ideally, you would solve the sufficient conditions. And in single variable, unconstrained, real valued calculus, that's easy. But as you begin to add on things like constraints, different variable spaces, or getting into infinite dimensional problems, that becomes less and less likely of an option. Option number 2, which sounds almost at first like it wouldn't work, is actually another even more common method. So instead of solving for those sufficient conditions, let's solve just for the necessary conditions. So then you find all the solutions for the necessary conditions and you analyze them with whatever abilities you have. Sometimes it's easier to evaluate the sufficient conditions than to solve for them. Or you could use other analysis. You could even just kind of look at your output. So you solve for all the candidate solutions to the necessary conditions, and then you assess all of those candidates. So that's a really widespread method for analysis. So widespread that the necessary conditions for a bunch of problems have become the famous equations that often define solutions. So I think, detailing mathematically the necessary conditions for each of these problems is a little outside of our scope, but you can at least know their names. So we've looked at, the not very surprising unconstrained finite dimensional optimization case. And in that case, the necessary condition is the 0 gradient. So perhaps you would, for an n-dimensional function, you would solve the equations of the 0 gradient, look at those solutions, and then see which one is actually the minimum. There are analogs for all of these other problems. So actually, I didn't include the discrete case here, but for constrained finite dimensional problems in continuous space, the necessary conditions are the famous KKT conditions. And so those use Lagrange multiplier conditions to take into account all your constraints. So the KKT conditions provide necessary conditions. And for that level of problem, there are some sufficient conditions. For each of these, you can come up with sufficient conditions, but they are more and more challenging. For the calculus of variations, the Euler-Lagrange equations provide necessary conditions. So any solutions to those equations are candidate solutions for your calculus of variations. And in optimal control, there's what's called Pontryagin's principle, and there's also the HJB equation. So that's called the Hamilton-Jacobi-Bellman equation. A lot of mathematicians in that one. So Pontryagin's principle gives you an ordinary differential equation, a system of ordinary differential equations. And if you solve it, you have a candidate solution. The HJB equation gives you a partial differential equation. And if you solve it, you have a candidate solution. I always thought it was surprising when I was learning optimization, how much of it is actually just using necessary conditions and how little you can use sufficient conditions for. So you're just coming up with candidate solutions. Also, every single one of these only supplies you with candidate local solutions. So again, the task of global optimization can be much more challenging. So I ran through those slides very quickly. I wanted to, at this point, take a small break and then switch us into a hands-on activity to look at some of the computational algorithms. So this will be a little shorter. I want to talk to you about the gradient descent algorithm And we're going to implement that on MATLAB and then look at MATLAB's optimization toolbox. But first, I'm going to open us up for questions, and then I think we should take about a 10-minute break and then return to MATLAB.